Hi, my name is Eric, and I'm going to talk about damping in a guitar string, and this is for Demo 3 in the Everything is the Same Engineered Systems class on Coursera here in the autumn of 2013. I'm going to look at a guitar string, a single guitar string, and the way it vibrates. I'm going to make an assumption that it's pretty simple, and I'm going to model it as a simple spring mass damper system. And that's not necessarily unfair. If you look at kind of the way you see you hear it when a guitar string vibrates, it oscillates and then it gets quieter with time, and as the oscillations dampen out, and eventually it stops moving and it's totally silent. There are a lot of things going on with a string. It vibrates at multiple frequencies based on its length and multiples of integral portions thereof. But really, the fundamental frequency, which is the string just vibrating between its ends, between the bridge and the nut, is that's the main frequency that you hear, in the main frequency that is of interest here. If you look at this waveform, we're going to assume that by superposition there are two ways, or two components. One is just a straight out oscillation with no damping, and that is basically the spring and mass portion of it. And then the other part is just the straight out damping part, and that is the damper mass portion of it. And if you superimpose those two, you get that general waveform. And so if you call this part A and this part B, the A part looks like x to the t is alpha cosine omega t plus, I don't know, delta or something, doesn't really matter. If you assume that this is evenly distributed across 0, then there's no offset, delta is 0. And if you assume that it starts at 1, at time 0, x is 0 is equal to 1 is equal to alpha times cosine of 0, because time is 0. That therefore alpha equals 1, and you have x of t is equal to cosine omega t. And I'm not going to really explain it too much here because we don't have much time. But this is the period of oscillation. This time here, this is 2 pi radians, and we know the time is based on the frequency, which I got through the software that measured the guitar output. And so the time for that is 1 over the frequency, which is 1 over 338. This is in seconds, is equal to cosine of omega divided by 338. And you know that for this to equal 1, because this is at 1, omega has to be equal to, omega over 338 is equal to 2 pi, so omega is equal to 2 pi times 338, and you'll see that later. And then the B portion is just a simple decay curve where x of t is equal to e, some constant beta times time, and that's what we're gonna figure out from experimentally in the next portion. And so if you add these two parts together, your final solution is x of t is going to look something like some sort of constant times e to the beta t, where we calculate beta later, times cosine of 2 pi 338 t. So moving on. Alright, so here's my guitar, and basically if you strum a string in the middle, it sounds and gradually gets quieter until you can't hear it anymore. And each string, of course, is a different tone. Alright, so for this next part, I want to show you the basic setup. So I have the guitar, and it's plugged into, the output of the guitar is plugged into this Omega interface right here. And what this guy does is it takes the electrical signal, the analog electrical signal from the guitar or from a microphone or other instruments, and then converts it to a digital signal that then connects to my computer through this USB cable. And then I'm using Audacity to do the recording. And then I'm going to switch over to a screen capture for the next portion here. Okay, I need to speed up because 10 minutes is going really fast. I recorded a single string pluck in Audacity from my guitar and outputted 100,000 samples at 44,100 hertz sampling rate into a CSV file, and then open that CSV file within R. I'm using R instead of Python or MATLAB because I'm running out of time, and I'm faster at R than I am Python because I have no Python experience prior to this class, and I don't have a MATLAB license. So R is a great language also. It's really powerful for some things like statistics and crunching huge matrices. But I hope to learn a lot more about Python, and yeah, but you're stuck watching R for the time being. So basically, I inputted, I brought in the data from the CSV file. I created a time column of time steps because it didn't include the time, and then I plotted it, and then I wanted to the maximum at that of this originally was 0.79, and I wanted to scale it up to get it to 1 so that this was nice and easy to work with. And so I scaled it based on the maximum value, and I've plotted it, and that's where I stand. And then, so this is if you assume that this is a logarithmic decay or an exponential decay of the form e to the constant times t power, you can simply estimate this by taking the natural log of the signal, which will give you then, it'll take that e to a power to just the power, so it'll allow you to look at this in a linear fashion. It'll just be a constant times time, and you can fit much simpler. And so that's what I did here. It gave me a warning message because of all these negative values. You can't take the log of negative values because e to any power will never be 0 or below. But that doesn't really matter because really we're only interested in the top values. Oops, here. So these top values here, this is now that sort of decay curve, which has been linearized, and it looks really nice and straight, more or less. And I don't really care about all this stuff because this top edge, the peaks, are what you sort of sense as volume, or at least of the guitar string. And then I'm going to plot the points and calculate slopes, or the slope. So I chose a point there and there and drew a line through them. It underestimates here in the middle. If you wanted to do this the next step better and had more time, you could write a script or program that would just pull out these peak values, and then you could do a line fit through those. In this case, this is going to be good enough for these purposes. Depends what you want to do with your model in the end on how close you want it to be. My damping equation and reprint it and not taking the natural log. You see that my exponential model is pretty close. It shows the general decay in volume with time. It doesn't quite estimate it correctly here in the middle, but definitely here in the beginning and toward the end of this set of samples, it does pretty well. And for the fact that we're not capturing so much that is going on in the vibration of a string, I'm not terribly concerned. This is not a true sinusoid inside. It's sort of a whole series of sinusoids with different frequencies on top of each other, and our model is just going to take into account this decay and a simple cosine sinusoid for the in the middle of it. There we go. So it's ugly because the sinusoid is so tight. It goes so many up and down so many times that it ends up filling the whole screen. But you get the point. It decays similar to the original signal, with a little bit of underestimation there and over here. And it actually overestimates down here. As I mentioned, it's not perfectly, the original signal is not perfectly symmetric about 0. However, for a simple model, this is really not that bad. And then the last step is to kind of undo the scaling I did, because you'll see the amplitude still goes to 1. The original signal, it only went to 0.79. So there we are. We're back to the original signal from the guitar, digitized, and then our model. And that's what we have in R.